Thank you, Ursula, for that introduction. Thank you, everyone, for being here today. And thank you to the Isaac Newton Institute for this wonderful opportunity to spend this time in Cambridge and to speak here today. When we ask, where did AI come from? There are a number of sources we could turn to for answers. Most obviously, there are significant bodies of published research that document the evolution of relevant fields and subfields. Much of that history is within living memory. And in many cases, we can still seek out firsthand accounts, and we have oral histories recorded with many of the researchers who've died. We have archives that enable us to glimpse research as it was practiced, and historians have begun writing scholarship that analyzes these developments and places them in context. But as a museum curator, I am especially interested in objects. There's no substitute for written records, but on the other hand, there's also no substitute for coming face to face with things themselves. The building we're in today has some terrific displays of mechanical calculating devices, original EDSAC and Titan components, and other relics from the history of computing in Cambridge. And these artifacts are illuminating because when we examine them, we physically experience the things that people lived and worked with in the past. So where did AI come from, and how can objects help us understand its history? Artificial intelligence is an abstract idea, and now more than ever, the models that drive it don't easily lend themselves to display in glass cases. But everything digital is ultimately physical, however difficult it might be to keep that fact in sight sometimes. In this talk, I'm going to use 4 objects to offer perspectives on the longer history of AI. They're a book, a piano, a calculator, and a mouse. The book and the piano are held in UK collections where I've worked with them pretty closely. The calculator and the mouse are in the collection that I currently look after at the Smithsonian's National Museum of American History in Washington, D.C. By approaching the history of AI through artifacts, we gain new perspectives on AI as something grounded in the material world. So first, I want to show you a copy of mathematician George Boole's Mathematical Analysis of Logic, which was published here in Cambridge in 1847. At first, this might seem like a cop-out. I just presented objects as a contrast to written sources, and this is very obviously a piece of writing. But it is not just any copy of that book. This is the author's own copy, and Boole has had the bookbinder insert blank leaves between all the pages. That's called an interleaved copy, and it gives him room to take notes throughout the book as he contemplates revisions to his system that he wants to make in his next book. It's held in Boole's archive at the Royal Society in London. It tracks his thoughts before publication and after, and it also tracks the thoughts of others as he recorded criticisms here and then responded to them on these blank leaves. One thing this object especially brings out, which will be relevant for other objects I'll talk about too, is how our human cultures of writing have been and remain deeply involved in projects related to mechanizing intelligence. Boole was a shoemaker's son who worked as a schoolmaster in Lincoln in the English Midlands. He never attended university, but he built up such a reputation by publishing mathematical papers that in 1849, he was appointed professor of mathematics at the new Queen's College in Cork, Ireland. It was right before receiving that appointment that he published this short book. It was his first attempt to represent logic in the symbolism of algebra. His work on logic is the historical source of what is now known as Boolean algebra and Boolean operators, logical words like and, or, and not. He represented each of these relationships as mathematical operations. And is multiplication, or is addition, not x is 1 minus x. Now, speaking in a computer science department, I'm confident that there are people here who know much, much more about contemporary Boolean algebra than I do. But you may find Boole's own system surprisingly different from what's named after him today. For instance, there is no negation operator as we would use. If you want to write not x, you have to write out 1 minus x. And for those of you who don't have a background on this, you'll get to encounter Boole's algebra as he introduced it, but don't worry, I'm not assuming any background and we will not get too technical. Logic in Boole's time paid great attention to what are called syllogisms. A syllogism is a 3-step deduction that combines 2 premises with a common term. So for example, all Greeks are human and all humans are mortal, to conclude something new. All Greeks are mortal. Aristotle first developed this method of distilling logic into words, and it was studied in various contexts for many centuries. Boole was at the forefront of a 19th century movement to literally rewrite logic by using equations, mathematical symbols instead of prose. So here's how Boole would write that syllogism. He represented all x is y by x equals vy. And for him, the variable v means something like the English word sum. So all x's are some of the y's, but may not be all of the y's. X equals vy and y equals vz. So you can substitute vz for y in that first equation, and you get x equals v prime z, or all x's are z's. So what's important here is that the algebraic substitutions he's making work the same way, basically, as substitutions in ordinary math. X does not stand for a number here, but when you're using Boole's system, you get to treat it like it does. You can convert what you're reasoning about into equations and then just follow rules that you already know. For him, this is the important thing. And he insisted the reason it was important was not because he expected it to be useful, but because he considered it evidence that logic is fundamentally reducible to mathematics. His next and more famous book on logic would be titled The Laws of Thought. He's trying to argue that thought itself is, on some deep level, mathematics. And his work would become highly influential, but readers tended not to accept his system exactly as it was. He found immediate pushback on all sorts of details about how exactly the algebra would work. Shortly after publication, he received a letter from his friend Charles Graves, a professor of mathematics at Trinity College in Dublin. And Graves had several proposals for improving the system. Boole took these seriously. He took the time to copy them out on the facing pages of his interleaved copy, and then he drafted these lengthy rebuttals, again, in his own copy of his book. So that's where this volume becomes such a richly layered source. It tracks the published ideas, and then Graves's reactions, and Boole's reactions to the reactions. Graves thought that Boole should introduce a symbol T that would mean the sum of all truths. He said, I represent the proposition either x is true or y is true by the equation x plus y equals t. And he goes on to explain the verbal interpretation of this is the cases in which x is true, x taken together with or plus the cases in which y is true, y, make up or equals the aggregate of all actually coexistent circumstances or cases, t. So the point for Graves is he's trying to make the equation more like a prose sentence with the math just kind of sprinkled in. And he's got these individual mathematical concepts individual concepts are translated into mathematical symbols. This is a technique that doesn't appear anywhere in Boole's writing. And Graves doesn't use the math to perform any calculations at all. The point for him is to use notation in order to sharpen the meaning of an English sentence. But he wants to make it as intuitive as possible with something easy to remember like T for truth. Boole's reaction to this is pretty blunt. I do not see that anything is gained by the introduction of T. And then he does a whole bunch of math that we will not go through step by step. And he uses algebra. He arrives at x minus 2xy plus y equals 1, which he concludes, perhaps a little smugly, is the form given in the book. So from the point of view of calculation, this symbol T hadn't contributed anything. It was redundant. It eventually just canceled out. And for Boole, those calculations are what mattered. An intuitive but mathematically redundant symbol doesn't add anything. But Graves wasn't after the same goal as Boole. Boole had thought he was introducing the definitive new way of writing logic, but his readers consistently wanted to modify his system and tinker with it. And really the way they followed him was just in reinterpreting logic as a problem of writing. This copy of this book is a physical record of human thought about that problem taking shape on paper through dialogue over time. It is also a book about performing processes of logical thought through mathematical equations. Formal notations were tools for making thought happen on paper, with laws at least partly taking over on behalf of the writer at times, determining what would be written next. Intelligence would not be trapped invisibly inside the mind. The next object that I want to talk about, the piano, was largely inspired by Boole's logic. It was designed in Manchester by the political economist William Stanley Jevons. In the late 1860s, he hired a young clockmaker, whose name I have not found recorded, to build a machine according to his design. It survives today, held by Oxford's History of Science Museum. The way it works is you type things like all A's are B's or C's, all C's are D's and not A's, useful stuff on the keyboard. And these vertical rods have different combinations of A, B, C, and D on them. And when you enter the rules, the rods move up and down so that if that cover is in place, any rods that have been ruled out by the rules that you've entered move out of view. So you can only see the sets of A, B, C, and D that are consistent with the constraints you've typed in. The capital letters mean something is included. The lowercase mean that it's excluded. So this piano was the centerpiece of the Imagining AI exhibit, which Ursula mentioned that we co-curated with others as well at the Bodleian Library in 2022. Today, audiences today, we're unlikely to find this machine convincingly intelligent. But in its way, it is evidence of strikingly prescient imagination, I want to claim. Because, okay, we call computers computers because they were originally built to compute, right? Meaning numbers, especially physics problems, often related to navigation and ballistics. And it was only later that engineers and users began to propose a wider range of cognitive tasks for these devices that had been built for number crunching. And now we've all got computers in our pockets, and I don't think the calculator app is the one anybody opens the most times per day. This widening of scope, the expanding of what things computers are for, is usually thought of as a 20th century story. But the logic piano shows Jevons was thinking beyond numerical computation a century earlier. He was insisting that his machine would not just calculate. It wasn't about numbers. It was about reason. And so at a moment when we hear so much about AI as this shocking new technology that will supposedly make the future totally unlike the past, in the exhibit, we wanted to use the library's collection to show viewers that techniques for endowing material technology with something that can be presented as intelligence has a longer history of its own. We've been imagining AI for a long time, even if we haven't always called it that. Jevons was inspired in part by Boole, in equal parts by Boole and by Charles Babbage. Babbage's famous plans to mechanize mathematics were extremely ambitious, but they were specific to mathematics. The whole of arithmetic seems within the grasp of mechanism, is how he put it. He wanted to automate number crunching to avoid the cost of labor that was involved in having tables for use in things like navigation and astronomy, tediously computed and checked by hand. Babbage's collaborator, Ada Lovelace, was the one to publish a detailed description of how the machine would solve a specific problem. And this chart here is sometimes called the first computer program, though there are debates around the technicalities of what that title entails. Jevons, for his part, saw all this and thought, okay, Babbage has concluded that anything mathematical can be mechanized, and Boole has shown us that logic is really mathematical. So he took the natural next step and argued that therefore logic can be mechanized. And he reported to the Royal Society, I quote, "By merely reading down the premises or data of an argument on a keyboard representing the terms, conjunctions, copula, and stops of a sentence, the machine is caused to make such a comparison of those premises that it becomes capable of returning any answer which may be logically deduced from them. The actual process of logical deduction is thus reduced to a purely mechanical form." You might object that this is a highly specific type of problem, that solving it is too artificial to represent deduction in a meaningful way. And not all of Jevons' contemporaries were convinced that his machine automated anything particularly worthwhile. John Venn introduced the famous diagrams that are named after him in an article that was partly arguing, this machine isn't that great, it doesn't do anything that my diagrams can't do. And he showed them. In debates like this, we hear echoes of those debates in discussions of AI today. Disagreements about whether a machine can reason are never just debates about what machines can do. They are about what it means for human beings to reason in the first place. Today, I think we are unlikely to find Jevons' piano startling. It is hardly perched on the cusp of so-called artificial general intelligence, but the glaring differences between our technology and that of the Victorians only make the rhetorical echoes more striking. We are not the first to be floored by the logical prowess of devices. And nearly a century before anyone began to suspect that the digital computer was destined for higher logical functions than mere computing, Jevons was looking at Babbage's engines and Boole's notations and arguing that a machine could do more than calculate by steam. His logical piano would actually reason. With the third object I want to talk about, we are entering the digital era. This is the prototype of Hewlett-Packard's HP 9100, introduced in 1968. It's from our collections at the National Museum of American History. This was the company's first calculator. Mechanical desktop calculators had been in popular use around a century at this point. The top left here is a Thomas arithmometer from 1867. The top right is a Monroe model from the 1940s. Those are both mechanical. But this sort of device was beginning in the 60s to face competition from electronic calculators, like those on the bottom there. At first, they didn't do a lot more than four-function arithmetic. They accomplished it by electronic means. On the left, we have a Friden, on the right, a Sony. And you can see they don't have very many buttons. The HP 9100, on the other hand, offered really significant computing power. It could do trig and logarithmic functions with the press of a button. Its dynamic range or ability to handle very small and very large numbers far surpassed existing machines of its size. It was programmable, and all of this fit on a desk and used only a manageable amount of electrical power. The HP 9100 also introduced many users to what became a hallmark of HP's calculators, reverse Polish notation, or RPN. Here you see one of the first examples given in the device's operating manual. Suppose we want to multiply 9 and 7. In contrast to the standard notation of arithmetic, which has us writing 9 times 7, here we multiply by first entering 9, then 7, and then we hit multiply. I want to focus on the required language of input for this calculator because it illustrates two things. First, logic and its notations, this tradition going back to Boole, continues to stand as a relevant and important resource when engineers are seeking to make machines do increasingly complex mathematical operations. And second, RPN highlights the ways that using an intelligent machine involves constraining your instructions to the form that will achieve the best results. And this is something we still see today. But before we say more about RPN, I'll say a bit about the original unreversed Polish notation so we can see where this name comes from. In interwar Poland, Jan Łukasiewicz introduced a system that he called parentheses-free symbolism. And here's how he writes the same syllogism that we saw at the beginning. All Greeks are human, all humans are mortal, therefore all Greeks are mortal. It is not obvious how to read that in orange, but it sure is concise. The notation consists entirely of letters, which play two main roles. The lowercase letters like P and Q represent propositions. So like variables in math, they mark a place where any specific proposition can be substituted in. Capital letters, on the other hand, denote what he called functors, or statements about propositions. So they tell us how the propositions are logically related to one another. And each capital letter functor is followed by what are called its arguments, the propositions that it describes. So the capital C stands for conditional, and CPQ means if P, then Q. A for alternative is or. APQ means P or Q. And crucially, then, you can make compound propositions by combining, having functors in their arguments serve as the arguments for others. And this can be built up into fairly complicated nesting functors and arguments. The thing to note about all this, not to get lost in the weeds, is that Łukasiewicz's rules are such that CAPQR is unambiguous regarding the order of operations. You don't need any parentheses. You can write these in to see first you would apply the A, then C to that result and R, but that's not strictly necessary. The letters by themselves contain the information about what order things should be done in. For contrast, we can see how Boole's notation would write the same thing. Łukasiewicz thought that this would be a very powerful tool for logicians everywhere. He also insisted that because it's only letters, even a basic typewriter can produce it, which is valuable. But it only really caught on locally, and it came to be recognized abroad as an emblem of the vibrant Warsaw School of Logic. Logicians elsewhere called it Polish notation. After World War II, computer scientists outside Poland found new advantages in Łukasiewicz's system. Its simplicity and its brevity are useful when it comes to writing efficient machine instructions. And as several researchers realized independently in the 1950s, it's even more useful if you switch around the order. So let's go back to arithmetic. In Łukasiewicz's system, he would have us write times 9, 7, right? He puts the functors before the things they're operating. But on the HP 9100, we write 9, 7 times. These instructions are perfectly ordered for a data structure that's called a stack. You put numbers in, and when you come to an operation, it is performed on the two numbers most recently placed on the stack. And this spatial arrangement conforms exactly to the order of operations that's encoded in Polish notation, provided you write everything backwards. The up arrow is here because the 9100 required users to manually move items up in the stack to make room for new entries, but later models would automate that process. HP would go on to make RPN the required mode of input on their scientific calculators for years. So this instruction style, modeled on a relatively niche logical notation, adapted in response to the physical constraints of efficient electronic computing, became pretty mainstream. Lots of people learned to use this in school. RPN as a consumer-facing input requirement might feel like a stricter demand than anything that we see in AI today. But the idea that there's now a growing expertise by the name of prompt engineering, it sounds a striking echo. Many users and researchers now claim that the art of phrasing prompts for large language models such that you get useful output is complicated enough to be described as a kind of engineering. It highlights the fact that effectively instructing today's AI is similarly not a transparent thing. We have tools making ever greater claims to intelligence. They always impose requirements of their own. If we want to control them, we need to meet them in the middle in certain ways. Finally, I want to talk about a pretty ordinary looking 1990s computer mouse. Unlike other objects I've described, this one is very much already prominent in any history of AI. There's room to debate its significance, as I'll get into, but cultural impact alone places it at the center of the story. In 1997, the IBM supercomputer Deep Blue defeated world chess champion Garry Kasparov. Chess is iconic as a game of intellect and creativity. For a machine to defeat the world's best human player sent a shock through popular culture. It seemed to indicate that computers may be approaching or even surpassing some kinds of human intelligence. This is the mouse that Deep Blue's operators used during those historic matches. A look at the history leading to the machine's victory shows how technological developments follow existing cultural paths. Games have loomed large in AI's history, and particular games have particular cultures around them that invite this sort of research. A practice of using board games as practice problems in AI goes way back. In the Imagining AI exhibit at the Bodleian, we displayed printouts from a checkers playing program that was written by computer scientist Christopher Strachey in 1952. His program was not unbeatable, but he found a way to code a decent opponent for a human player. As an interactive program, this is also one of the earliest video games ever made. But chess soon emerged as a more compelling focal point for a lot of researchers. In a 1950 piece for the popular magazine Scientific American, mathematician and electrical engineer Claude Shannon proposed chess as an arena for study. This was still several years before the computer scientist John McCarthy would coin the term artificial intelligence, but it belongs to that emerging field, which McCarthy would so effectively brand. And I know Tom has a lot to tell us about that branding process in a little bit. So Shannon explained, the chess machine is an ideal one to start with for several reasons. The problem is sharply defined, both in the allowed operations, the moves of chess, and in the ultimate goal, checkmate. It is neither so simple as to be trivial, nor too difficult for satisfactory solution. And such a machine could be pitted against a human opponent, giving a clear measure of the machine's ability in this type of reasoning. By working on a sharply defined problem of appropriate difficulty, in which progress can be easily measured, researchers would learn generalizable techniques for getting computers to do complicated things. It was important to make this argument because in 1950, there are still very few computers in the world. Given their scarcity and expense, Shannon knew that Many readers would find it frivolous to suggest using these scientific and military instruments to play a board game. He acknowledged that teaching a machine to play chess was useless in its own right, but he insisted it was worthwhile for the sort of basic knowledge and technique that would be gained. And indeed, AI chess became an active pursuit. By 1965, Russian mathematician Alexander Konrad could describe chess as the Drosophila of artificial intelligence, a metaphor that would be often repeated, and it contains several layers of truth. Drosophila melanogaster, the common fruit fly, is the bedrock of experimental genetics. It's a classic example of a model organism, one that is not especially important to human beings in its own right, but it's received disproportionate scientific attention because its features make it especially convenient for certain methods of study. In the early 20th century, Thomas Hunt Morgan, a professor at Columbia, started experimenting on Drosophila. He was looking for evidence that evolution is driven by heightened periods of mutation. The flies proved very easy to work with, easy to store in the lab. They kept them in used milk bottles they could pick up for free from door stoops. This was the era of delivery by milkmen. And the flies reproduced very quickly. So the whole thing was cheap and efficient. Now, this sort of logistical concern doesn't really feel like part of biological theory, but it ends up exerting enormous influence. And similarly, chess was a convenient choice for reasons beyond the intrinsic ones that Shannon had identified. Chess lent itself to AI research because it had this robust existing culture of tournaments and theory. There were books and books full of example openings and games and endgames. There were formal systems of symbolic notation for describing games in writing, systems for ranking player skill, an established culture of playing by mail, so the idea of facing off against an opponent whose face you can't see wasn't weird. And all of this intellectual infrastructure was already there for AI researchers to take advantage of. Just like fruit flies were easy to bring into the lab, chess was easy to bring into the computer, because in many ways it was already conceived computationally. Back to real Drosophila for one more moment. Morgan never did find evidence of those heightened mutation periods that he thought might occur, but he found something else. Mutations were occurring at a normal rate, but with so many flies, the researchers were able to discern patterns in the inheritance of those mutations. Morgan and his students documented correlations, determining which traits were linked more or less closely, and in doing so, they invented genetic mapping. Morgan had launched his Drosophila research program to pursue evolutionary biology. He wanted to study change over many, many generations. But the flies pushed the research in an unexpected direction toward the details of how specific traits pass from one generation to the next. The historian Nathan Ensmanger has observed that the Drosophila metaphor for AI in chess, it doesn't only capture the ways chess was a productive focal point. It also captures this unintended quality that objects of study can pull researchers away from their original goals. In the case of Drosophila, that unexpected pivot was also enormously fruitful. In the case of AI chess, though, that's more debatable. Chess came with a robust tournament culture, which shaped the landscape that researchers worked in. These photos are from computer chess tournaments, which followed the existing model of human chess tournaments. As the word tournament implies, they were about winning. The culture incentivized researchers to ramp up computational power and pursue brute force approaches when they yielded results. A brute force approach in computing or mathematics is one that doesn't bother trying to be clever and just says, okay, we're going to check every possibility. In chess, that means rather than striving to encode a deeper understanding of chess strategy in your program, you just perform relatively basic analysis of as many moves as you possibly can. But brute force analysis of millions of chess positions does not tend towards Shannon's first goal of learning generalizable techniques for using computer intelligence effectively. The AI pioneer John McCarthy, for one, saw Deep Blue as the culmination of a distraction. Writing in Science shortly after the computer's victory, he asserted the fixation of most computer chess work on success in tournament play has come at scientific cost. And he invokes the famous Drosophila metaphor again, lamenting that computer chess has developed as genetics might have if the geneticists, that's Morgan and his students, had concentrated their efforts on breeding racing Drosophila. We would have some science, mainly very fast fruit flies. So the pull of tournament victory by brute force had drawn attention away from McCarthy's priority of better understanding the nature of intelligence involved in playing chess. The Deep Blue supercomputer was housed in 2 towers. It consisted of 30 processors, each of which controlled 16 customized chess chips. It's worth noting that this reliance on parallel processing across 480 specialized chips, it does represent an approach that has become extraordinarily important in AI, and it could be argued that there's research value here on the hardware side. The ultimate significance of Deep Blue's victory is definitely open to debate from a number of angles. We do have one of those processors in our collection at the National Museum of American History. But I chose the mouse as my focal point because it reminds us to picture a human operator, the mediator between the computer and the game board on the table, and by extension, the mediator between the computer and its human opponent, Kasparov. Like the calculator, it points to the necessity of interaction and control. The human operator must convey information about Kasparov's latest move to Deep Blue and direct it to select a next move. But the control goes both ways. It's Deep Blue that controls the operator, ultimately, dictating the next move they make on the board. Deep Blue was not the last major AI milestone to take place on a game board, as I think in this department is well known. In 2016, Google DeepMind's AlphaGo defeated human Go champion Lee Sedol. And this department's alumnus, Demis Hassabis, is, of course, a leader on this project and his work that's closely related to AlphaFold, for which he recently won a Nobel Prize. Go is a strategy game invented in China several thousand years ago. Players take turns placing stones of their assigned color on any open space on a 19 by 19 grid. The goal is to surround as much territory on the board as possible. And if you completely surround one of your opponent's stones or a connected group of stones, you capture it. The rules are very simple, but they lead to incredible complexity. There are more possible board positions than atoms in the universe. Whereas brute force could propel Deep Blue to victory, Go was always going to require more than number crunching. So AlphaGo's victory is instead emblematic of the rise of deep learning neural networks, the approach to AI that powers all the sensational new products we hear so much about today. Once again, AI garnered major public attention by playing a game. And in particular, once again, a game with a robust culture of theory and tournament play. A game widely seen as a symbol of intellect, creativity, and even genius. AI continues to develop along these lines that are prepared by existing human culture. Technology does not appear in a vacuum. To wrap up, we've covered a lot of ground, and that in itself is part of the point I want to make, that the history of something like AI is tangled up with any number of other histories that we might not expect to be relevant. And objects can help bring that out. The book shows how writing, and especially formal notation, could already be seen as something that materializes thought. The piano shows that the history of reasoning machines, as distinguished from the better known calculating machines, also have a much longer history than the digital era. The calculator shows how communication with machines is not straightforward. It's subject to constraints and draws on unexpected resources. Choices must be made about how we control these devices. And the mouse highlights a particular history of game playing in AI, and a culture that offered convenient avenues of research while exerting its own influence on where that research went. Together, these objects sketch a longer history of our efforts to mechanize thinking. They suggest ways to understand the technology that's shaping our current moment as rooted in long historical developments and grounded in the material world. This is important, especially as every day it becomes easier to imagine AI as immaterial. The data centers are far away. Interacting with AI models on our phones gets more and more mundane. The interface and the material stuff, these things can almost become invisible. But AI is always material. It can only be developed along the lines available in a given culture. And remembering that these histories are older than we might think can help us see past the illusion of unprecedented technology that would somehow arrive fully formed to shape the future for us. We, in our past and present, shape technology, even as we so often then conform our practices to its constraints. We should do none of this absent-mindedly. Thank you.
Thank you, Dave. Okay, that's fascinating. I haven't heard the truth fly now before. Questions? Ulrika.
Yeah, what's wondering, I mean, you stopped basically at the beating of Go champions. Is that what we call modern AI, or is it just one step before ChatGPT, etc.?
Right. That's a good question. And I think it is not one that has any settled answer, what we would consider modern AI. I think it's a designation that depends a lot on the sort of purposes and goals of the person defining when modernity in AI starts. And I don't think this is unique to AI, but drawing that sort of line has to serve some sort of purpose about saying, these are the things that we recognize as ours and productive and valuable. And maybe the past could maybe be seen as formerly productive, but I think if when we try to carve off a clear break, I would always want to ask sort of what is being left on one side of that, and why? What is the point of leaving something out of modern AI? No, I didn't mean to suggest that you were doing it, but I think that that's the sort of question or those sorts of timelines are always shifting. Modern is always sort of what people see as new, and the answer will continue to change as people have sort of new goals and are excited about new things in AI.
I enjoyed the lectures.
Thank you.
Are there any questions?
Can you shout it in the thing?
Sorry, are there any online questions?
Yeah, if anyone has any questions online, just put them in the chat.
I was going to ask whether you have examined whether there is a history of not relying on a goal.
Not relying on a goal.
On a goal, yes.
Well, so the short answer is I personally have not examined that. It's an interesting question because on a certain level, to do something, you must have a goal. So I would think, or how?
Fred, I hoped you might lead on is artistic creation.
Right.
Where I suspect many artists would say they have a goal.
Right.
A particular set of steps. That's why.
Yes.
That's what
right. And I would agree with that. I would sort of I guess then was thinking of goal in the general sense as if the goal is to produce a work of art, but then the process might be, or I see you shaking your head, and right, that's an interesting question in itself. But so is something like that sort of artistic approach that is less goal-oriented, is that something we find in science as well? I think a lot of advocates of basic science might want to make a similar claim and say, there is a sort of pursuit of knowledge for its own sake that does not need to be guided by a goal. And there's also a question of how strictly held a goal must be to count as a goal. For thinking of the example of Morgan with the flies, he responded to the change. It's not as though he dug in and only continued asking his original question. He had the creativity to realize that other knowledge was available in the work he was doing and reorganized his work around that.
Yeah, question at that.
Do you see current interest in using AI to advance mathematics research as related to this tradition of interest in AI research in solving kind of very deep human games, as it were?
Yes, I do think of the things I've talked about, I think current efforts to develop AI that would be useful and interesting to mathematicians and sort of provide answers to the questions mathematicians ask is much more closely related to the game playing than it is to something that on the surface might seem more connected, like George Boole was a mathematician and his other books were about differential equations. But the difference is there, in that earlier work, though it's more sort of superficially connected to mathematics, it's about making an argument that the mind somehow is mathematical, and it's not about actually getting at new mathematics that will change how analysis or algebra is done. Whereas with game playing, especially recently, AI that plays games like Go and chess has gotten so strong that it now, very high level players interact with the AI in order to learn about it and observe it and see how it can make their own play better. And so, yes, I think that is one of the closer analogies to what mathematicians might hope for, those mathematicians who are excited about AI methods.
Great question. And a quick plug for the Newton Institute. You can learn more at the workshop at the Newton Institute on big proof, which is June the 9th to the 13th. Let's see. We are out of time, though I can see there are lots more people with questions to ask. So, thank you very much indeed, David.
Thank you.